So while we are putting everything on the screen, thank you to everyone that has written a question. So I've counted about 15 questions that we wrote in 30 minutes. So that's about a rate of 1 question per 2 minutes. So at the end of this meeting, we should have produced hundreds of questions, which will be a good opportunity to meet again soon, I suppose. So we have an hour and 15 minutes. There's almost impossible to go to all the questions, so we will randomly pick some of them. And if at some point you really want to talk about one of those questions, feel free to shout and help us orient the discussion.
Yeah, just to add, I well, not randomly, but I roughly grouped them in 3 topics: so stability of mass transfer, then a bit the observational point of view, and then additional processes. So just so that you have a little bit of an idea of where what's coming. Maybe we can start with something on top here. So I think the first question, I don't know who wrote it on the blackboard. This is a blackboard question, but I like to start with this one. So we talk about stability of mass transfer all the time, but how good or how bad are we really in this? Who would like to dare to say something about that one?
Something that we do very bad with that propagates uncertainty often in rapid codes is we do fixed mass transfer stability as a function of temperature, radius, and luminosity, as long as it's in the right phase, which is usually said like, it's on the Hertzsprung gap, so it's going to be this, and it's on the giant branch, so it's going to be this. But I think Hugues made a really solid argument that if we don't move beyond that assumption, then we're really pushing uncertainties forward in all of our population models.
Go for it.
Well, I would say that, like, if I had to pick a number between factor of 2, 10, or 100, I would say geometric mean between 10 and 100. So 30, factor of 30 uncertainty would be my guess.
Mass ratio?
Yeah, mass ratio is just huge.
Like, do we agree with that? Because I think a factor of 30 in mass ratio uncertainties.
That's to the second question. Like, that's a factor of 10 is a lot.
Yeah.
I don't know. Is there a number?
You're limited by the second question.
Yeah,
Right.
yeah, that's a good.
You're always limited by the second question, which is about 120 to 130. But the point is that, say, you're coming from uncertainties that we have as people who evolve binaries through the mass transfer to those who study the dynamical stability through Darwin, and they're a little bit more certain than us. So you can definitely say that your mass ratio, like 1, you're still stable, and 110, maximum 112, you are unstable. So that is your range. That you definitely can do.
Doesn't that depend on evolutionary phase, for example?
For Darwin, very little. Darwin is a mechanical instability. Now, it depends on the structure of a star, but that can be way better calculated because it can be obtained for any concentration profile. So your limit is limited. So you don't have infinite uncertainty. Whether it's good or bad for you, I don't know.
Can I ask more question on this? Does that mean that there is no binaries with a mass ratio smaller than 112? Because it's becoming unstable? It has to be
For Ursa Majoris, no.
What do you mean Ursa Majoris?
Okay, this is binaries where most of the low mass ratios are known. The Ursa Majoris are binaries feature like population size and best known for the distribution of mass ratios. And I think 112 is exactly about the minimum that they have.
There should be a separation.
Yeah.
But Natasha, you said Darwin-Riemann instability, or which instability?
Darwin.
Are we talking about the same?
Darwin? I'm not
Yeah,
very good at-
yeah. I don't know.
You know, like it's almost the same as Charles Darwin, but pronounced
Yeah.
incorrectly.
Yeah, but that also has to do with tides, right? So if you would have a system that's very wide, it can still have an extreme mass ratio. It's just not close to mass transfer, right? So you said, are all binaries with a high mass ratio unable to exist? That's not the case. It's just when
Oh,
you're.
no. I mean, it's when they actually able to exchange their angular momentum, yes. But here is speaking about the mass transfer, so they are close.
Lieke?
Follow up to that. That was also my question. So you're now saying that basically those Gaia BH1, BH2, and H1 can never have had stable mass transfer, assuming that they at some point mass transferred with this mass ratio of 20 to 1. And then that means there must be unstable mass transfer that doesn't shrink the orbit, or not, because it's definitely more than 1 to 12.
They transferred mass.
Well, there were the argument on my side was you have stars that
So the
were
donor's been radiated.
there was a
So
one solar mass
112
star.
is for Ursa Majoris, which are very close to the polytrope 3 halves, right? When you move to more radially concentrated, you are able to
Okay.
derive a different limit, which usually is not within the interest of a community who usually studies the
Yeah.
limit.
So how much can we push it when we have radiated?
I mean,
envelopes?
it's actually a function basically of duration radius. So you can look up a paper, plug in the different duration radius and find the mass ratio.
Sorry, could you repeat
It's
that?
just a function of a duration radius. Find the duration radius for your star, plug into the for formalism, and you find the mass ratio.
Katie wants to say something.
So I just,
Sorry, you are also.
I know, I'm sorry. Such a curmudgeon about the black holes. I think that because the companions are one solar mass, the dynamic range of accretion, like you have to do something with the mass if it goes stable. Like it can't not be not accreted. And if they're 0.8 or 0.9 or 1 solar mass stars, like how much? But like you're gonna lose 20 solar masses of material, or like none of it gets accreted. I think that's the.
That would be.
I throw my hands up.
I don't know.
Maybe that segues quite nicely into the third question there. So what are the important parameters, the stellar parameters that matter for the mass transfer? Are we considering everything that we need to consider? Brian.
I mean, one thing that can be, potentially relevant in short period binaries is, of course, irradiation from the companion. So, in addition to the instantaneous radius mass position of the donor, you could also consider some type of external flux from either the accretion disk of the transfer system or the accreting star, maybe. I'm thinking of this is relevant in CV systems, but I imagine it could also be relevant in other contexts. This comes back to what is the effect of the radiation on the mass transfer process, or generally, but I think also just the fact that the star has to radiate its own nuclear luminosity as well as whatever it's irradiated with from the outside can be relevant in some cases. So if one were to add an extra dimension to Hongwei's plot, I would say maybe radiation flux would be an interesting one.
Pablo, were you raising your hand?
Oh yeah, I guess it's just a quick reminder. I guess many people know here, but it's not just the properties of the star, but also how the mass is transferred or ejected from the system.
So that's like the fourth point.
Oh, sorry. I do not read so far.
Good
it
segue
seems.
into question 4.
Sorry for that.
Oi.
I just will add, like in the past, I've been arguing against alpha, gamma, etc. formulas for common envelopes, and we are going to that direction. So here, I just want to say, guys, it's time to forget about mass radius exponents. I mean, the point is that when you speak about mass radius exponents, for example, you take for dynamical transfer adiabatic response, which is never achieved. And in reality, if you plot the response, where it will be a function of a mass transfer at this moment, and it will be anywhere between adiabatic and thermal. And it's actually quite a range. So whenever you try to use the mass radius exponent, you're doing that.
Oh yeah, sorry. I had also still a question from also earlier, but it's I think it's very related. So like, I was also interested that there was always this idea of like, oh, there's these critical mass ratios, for instance, under which like there is stable mass transfer or not, and usually it's like kind of like factor 3. And I know I already see Natasha being like, okay, we kind of knew that wasn't true, but then of course there were like, you know, many papers, including Pablo's and so on, but also like, for instance, Van de Heuvel 2017 and Pavlovsky, where like people show like, okay, it really depends on like the structure of the envelope, like convection or not, and that these mass ratios or critical mass ratios are definitely not true. So like there they find like, I think mass ratio of at least 10 or so. So is that, I guess I wonder, like, are we going to find in the future that 12 is also exceeded? Is that like a more strict limit, I believe? Is this like 10 only in rare cases, or is it quite common? I'm curious what people think about that.
Well, because Pavlovsky was my student, I can comment on that. So, I mean, at the time, the further we go in mass, then the bigger mass ratio was, because the stars will become fluffy and fluffy as you increase the donor mass, and more concentrated towards the center. So I think there will be the limit. You cannot push it. I mean, whatever you do with how well you try to do the mass transfer, there always will be the limit to what star is. So, but those critical mass ratios, they will be not just the numbers, right? I mean, you can think about some continuous function of mass ratios, periods, and so on, but it's not the numbers.
But to that, I would also add that when people are able to do a 3D radiation hydrodynamic simulation of an envelope, the density profile doesn't look like a 1D model. So I think all these questions are important, but we should probably revisit them with better quote unquote stellar evolution models.
Yeah, but 3D profiles also have problems of resolution, especially with super adiabatic layer on it.
Resolution problem in 3D profiles.
I think one of well, one of the things that Katie reminded me of is these critical Qs have another problem, right? Because the critical Qs are bad in itself, but calculated for conservative mass transfer. So if you make, I don't think any of us believe that mass transfer is always conservative. So if you actually assume that mass is lost and in different ways, in a different angular momentum, that will actually shift your stability boundary as well. That raised many questions.
Yeah, I fully agree with that, because it's something I want to show tomorrow, and you might have seen it before, but we find stable KC mass transfer purely because your mass transfer is non-conservative. And I think it's something similar to what Pablo said, maybe not entirely the same, but you need to really look at how your orbit reacts to the mass transfer for your stability, not just a star. You cannot treat it as an isolated thing. And I just want to say that I really do not agree with people who just use a fixed mass transfer rate to say it's unstable. Again, not saying that I have the answer for that, but one thing that we try to do is see if it becomes like faster than thermal, for example. That's already one way to go, but if you don't use the hydrodynamic mode in MESA, you cannot go to dynamic situations. So you have to work with what you get, but yeah.
Maybe one thing to add, but people can correct me if I'm wrong, because I put this here quite provocative, saying that mass transfer, in some papers assume that mass transfer is unstable once you hit this mass transfer rate higher than 10 to the -4 solar mass per year. But I wonder if it's actually wrong interpretation of the current of us, right? Where people actually made the remark the other way around. We know it's stable below mass transfer rates, below 10 to the -4, and we're just not going higher, right? So we're limiting our model to 10 to the -4. We're not saying anything about what's happening at higher mass transfer rates, and we just assumed, okay, but then it's unstable. Yeah. So
Is it so defined as unstable in population synthesis? Because it's
no. So this is in detail in some older works that try
Older,
to
yes,
that try to assess the stability of mass transfer. They said, okay, we go to 10 to the -4, and likely it's going to be unstable above it. You know, if you take that, then if you just look at the results and you adopt that, you would just say that all of these systems are unstable, while that's maybe not what the initial paper tried to say. It's just we did not simulate mass transfer rates that are higher than 10 to the -4. But it's kind of the question, how do we define stability? Because I know, for example, in the Tamming paper, that there is multiple criteria and they give different stability limits and even like different trends in the stability limit. So when we say mass transfer is stable and we calculate with the best codes of the world, do we even agree on what the definition of it is?
As long as you can still apply Roche slope, or basically what you don't have Coriolis force too strong, then it's fine. I mean, if you can calculate, I mean, after that, it's not really question about stable, unstable, it's just invalid.
Yeah.
I have a really quick follow-up. So from the things that you just said, I always assumed that if the mass ratio, the mass ratios are calculated, and for conservative, this is the ratio of where it's unstable. But I always thought that if it's less conservative, the mass ratio becomes more unstable. But you're just saying the opposite. Sorry, sorry, it's so many. So I always thought I could see it as an upper limit of stability, being like, okay, well, at completely conservative, these mass ratios are the limit of.
It depends on your angular momentum loss mode, right? That's going to push you in one direction or the other.
I thought it was always more unstable if you have less conservative.
If everything goes through O2, it's very unstable, everything, for instance, in the limit. Well, I just want to make a small comment regarding just grabbing a boundary in mass ratio, for instance, and using it in rapid pop-synth. You have to be careful that it's not as simple as a star of this mass and this radius has a given mass ratio boundary for instability. It depends also on the structure of the star in the core to envelope mass ratio. So if you grab calculations done by someone and then you apply them, for instance, in DSE, which has completely different stellar tracks, it can give you very wrong results, even if you think you're doing better.
I'm so in with that.
So given that a lot of pop-syn codes use the Hurley tracks, like can someone drag up Eggleton's code and calculate stability then again?
Well,
Not me.
There was a question from, there are two questions from that side. Let's go there.
yes, let me know what it's.
Well, already. I should think from as an outsider, I'm confused. A lot of times people use conservative mass transfer in different ways. Some people just mean that all the mass is not transferred. And I think of it as, how well conserved that total angular momentum is, how much of the transferred angular momentum ends up back in the binary. But anyways, so I was thinking, it would be useful. I mean, if there really are these parameters, the question I think to me is like, what is the minimal number of properties of a star that could define this critical Q that you could measure it for? So we've decided it isn't just the mass and radius, it's also the structure, but maybe can you say there's a core mass, an envelope mass of this size? I mean, are there a minimal number of parameters that could actually create a more useful grid? Or is it just impossible and never be able to put this into fast pop-synth? I guess I'm just curious people's thoughts. It seems like the state of the art for some of the codes is very, very primitive to me compared to what could be done, but people seem to be saying what could be done is maybe not enough, I guess. So that's sort of my question for the room is there a way to make a better prescription that isn't the full thing?
Pablo, want to jump on this?
So I mean, in the most general case, you need like the entire abundance profile and the thermal state of the entire star. So it's like infinite dimensionality. But
for perfect accuracy, the question
yes,
you get better than
I think it needs to be studied, and it is being studied in particular by that person that's sitting over there, Anakera.
Okay.
And talk tomorrow.
No, she doesn't have.
So one point that I wanted to raise regarding the Tamming paper is that the Tamming paper actually states that we are not really identifying the onset of unstable mass transfer, but rather we're identifying stages in which 1D codes, well, the assumptions of the 1D codes fail. So for example, when mass transfer, like the orbital evolution is too quick, we have fictitious forces which should arise, but then the codes are not tracking them down. And if the mass transfer rate is very high, then as we said before, with the radius exponents and so on, we're not we're ignoring other effects inside the star evolutionary code. So I just wanted to raise the point that whenever we say that mass transfer turns unstable, we're not really saying that it's it's the beginning of common envelope evolution. It's just that the code is not really adept for this sort of, for tracking down this stage. So we really need 3D hydro simulation probably to better pinpoint when this happens or not. I mean, I also have questions about this.
May I add something to this? So if I may add something to this, I think if people say that mass transfer is unstable, they can mean two different things in general. Either that this is a runaway situation that really leads to the common envelope evolution, or that it's just unstable on the thermal time scale, and then it doesn't have to lead to the common envelope evolution, but it can just happen on a dynamical time scale, but the system can still survive. But I think from a theoretical point of view, if the mass transfer is happening on a dynamical time scale, it's hard to say something with a high degree of confidence with these one-dimensional models. And so, yeah, a more general comment regarding this topic is that in general, mass transfer can happen on three different timescales, either the nuclear timescale of the donor, then the thermal timescale and dynamical timescale. And I think in general, these mass radius exponents are a good indicator of whether the mass transfer is stable on a thermal timescale. And so, for example, for this system that would have a mass ratio of 20 to 1, the mass radius exponent of the Roche lobe is 40. I have checked it up in a book written by Peter Eccleton on binary stars and multiple star systems. And I think in general, it would be hard to find an envelope which would survive this on a thermal timescale, but it's not to say that it necessarily needs to lead to common envelope evolution, because it's also the case that if we had binary mass ratio of 100, then so for example, the donor is 100 units massive and accretor 1 unit. And if the donor loses 1% of the mass, it doesn't do much dynamically to the donor, but it changes the mass ratio by a factor of 2, for example. So it's, I think from a theoretical perspective, if one isn't really modeling a specific case with a three-dimensional code that includes all of the known physics, it's hard to say how this will go. So it's important to observe and see like what happens in nature, and then try to explain this. And yeah, so that's my comment to this. Maybe that's a good transition moment to go to observations.
Maybe I can say one more thing.
Go.
The provocative of standing here, but I think we kind of heard comments along one direction a couple of times now, which is the breakdown of the model does not mean that mass transfer becomes unstable, right? The breakdown of the Roche lobe model does not mean that it's stable or unstable, just means that our model just becomes not good enough to describe science. But at the same time, that makes me a little bit pessimistic that we can make progress. Can anyone convince me that I should not be pessimistic? Because the Roche lobe model is breaking down, this is breaking down.
But usually it's related. See, I mean, it's breaking down when you have a dynamical timescale mass transfer. So, I mean, you get it at the same time as you get a dynamically, at least dynamical rate mass transfer. But that's the only way how it can start to change on the timescale where the Corollas acceleration become important.
So I would say I would be a bit more optimistic in the sense that at least we can say, till this point, we can use our methods. So we can predict at least what a fraction of binaries would do. And we can use that for constraints. We're missing a fraction, the common envelope, that can do whatever they want. But on the other side, maybe we can say something more concrete.
Nice.
Sorry to bring this in at the end. I have a little bit of a naive question, and this comes into the structure of the stars themselves. What impact does metallicity have here? So I'm thinking, yeah, you have ultra metal poor stars, and or just assume you only have opacity from electron scattering. Can you get more extreme mass ratios? Does anyone have any idea here?
I would guess it hasn't really been studied in detail, but I would expect it to have an effect because it changes significantly how, for instance, when your core is contracting after the main sequence, the radius of the star will be very different with the metallicity at more or less a given stage of contraction. And that will affect how the star responds to mass transfer. So I would expect there to be a C dependence in those ranges.
R and then maybe Z. Well, I mean,
M, R, or Z, that was the question.
And core mass versus envelope mass. So you just increase dimensions.
Well, it also depends because you have like different levels of luminosity, and so you get also super Eddington in some other areas for your envelope. So of course your envelope behaves kind of differently depending on which metallicity you're considering, but not also metallicity, also the internal mixing that you're considering. So luminosity levels can vary quite a lot, and therefore you can expand more or less your envelope and therefore forming convective areas or radiative areas, and still, yeah, survivability changes and also initiation.
You want to do observations because it's kind of segueing into.
I just was trying to feed the other third of the room, but we can
do a show of hands. Shall we talk about observations? Are we going to talk about additional processes? So observations.
What was the second?
additional processes.
Yeah. Additional processes. Okay, clearly observations. It is. So do we have any hope that observations are going to help us to determine the stability of mass transfer? And which observations would it be? Are we thinking gravitational waves? Are we thinking electromagnetic? Are we thinking high mass, low mass?
Definitely not gravitational waves. Way too rare.
Well, E.T.
Just a naive question here, but how easy it is to observe like post-mass transfer environments?
It's hard.
Okay, but let's define hard together. What's the major issue here?
That's okay. Does October have a talk on that?
So we basically, the observations we have for most massive stars at least are in the Magellanic Clouds. It's very hard to do it in like the Milky Way because you need to know distances, extinctions, things like that. And in the Magellanic Clouds, having resolution enough to see the environments is a bit difficult. That being said, we do have a source that seems to have a nebula around it. From like the spectra, there are some like intensities above and below like the actual spectral line that makes it seem nebulous. But that's kind of the most I've seen as far as the environments of post-interaction massive stars.
How about low mass?
I want to ask, what kind of environments do you mean? Like, what are you after? Circumbinary disks or?
Yeah, just constrain, also circumbinary disks, but in general to constrain somehow the environment, yeah.
So, yeah, as Bethany said, I guess for circumbinary disks, you have some constraints from interferometry. So there are some really interesting systems where you see evidence for this. I don't know whether the constraints that are obtained are sufficient to constrain whatever it is that is necessary for all those complications. Yeah, I don't know. I will be talking a little about post interaction from observations, but not so much on environment. So,
Floor.
Yeah, so I was also curious, what about systems like SS433 or like the ones where we resolve some mass transfer observations? Like, are we confident about just mass rates there, mass accretion rates, and what it tells us?
I don't want to talk too much, but I guess I can say something. So as far as I know, SS433 is infinitely complicated, like trying to infer anything about it. One thing that can be done with, and I think it's been done for SS433 is essentially you can try to measure a period variation, convince someone that you've observed it, and then you can try and convince people that you know the masses of the stars, and then you can say something about more or less how this period variation relates to a mass transfer rate. I think particularly for SS433, all of that is very shady, all those steps.
I would also add that when you have a compact object, the accretion on the compact object and how the mass might be rejected by the binary may be different than if you have a puffy main sequence star, right? So it's not clear to me that SS433 is the right Rosetta Stone to understand this.
You could just quickly say what it is for the...
Yeah, fair enough. SS433 is an X-ray binary with 12 star mass donor and a black hole. I don't remember the mass.
3 solas or something. It's...
Well, and it shows also like there is a nebula that seems to have been carved by a jet coming from the accreting compact object over 10 to the 5 years or something like that.
And it's very good to have L2 outflows and like,
Yeah.
I mean, it has everything.
Yeah.
Microquasar, super-reading too.
Yeah, I had a question on the previous thing, so if Bethany wants to say something as a follow-up to this, she should go first.
Yeah, just about X-rays for like compact objects, because I have a few accepted Chandra proposals for massive stars and binaries of compact objects. And like the two main unconstrained parameters there would be the winds and also the efficiency of the mass transfer onto the compact object. And both of those things are not like super well understood. And so like I'd be like really open into hearing like how you could then get to stability from there if those two things are a little bit difficult to interpret once we do have an X-ray luminosity from that.
So I have a question more on before when we were talking about the populations of observed systems that are certain to have mass transferred. So we know there's the stripped stars. Then we know there's some white dwarfs that are post-mass transfer. Does anyone have a good overview of what are all the populations that we have? Has anyone ever done an overview or review of post-mass transfer observed populations? Should we start it?
Wait for the end of Gaia.
Yeah, but then, yeah, well, Gaia is also a specific, very biased, it's a biased population still.
It is, but it's going to be much better later because there's still hardly any binaries in there, relatively speaking, and there's going to be a lot more binaries in the later data releases. So I think it'll be much better then at least, and there'll maybe be some triples as well.
What about alcohol?
So in like to add on to Lige's, I'm really interested to see the new Chara survey, 2-year survey. I think is going to have a lot of papers coming out of that, and to see how like, since they were able to resolve beta Lyrae, if they'll have papers coming out that will maybe answer that a little bit, is what I'm hoping.
The reason I shouted Gaia is because if we're doing comparisons between data and observations and simulations, you have to do selection functions properly, and selection functions of spectroscopic surveys are really, really hard to map unless you know what their selection was. And that's why I think Gaia is the future, because we can all do Gaia selection functions much more easily than compiling like 60 different subsets of different populations and trying to work out the selection functions of all of them together.
I 100% agree, but won't that intrinsically bias us then to only look at the things that are easy?
I'll repeat. So the question is that Lieke completely agrees, but she's afraid that this will make a very strong bias towards only looking at those systems that are easy to find.
Gaia covers the whole HR diagram. So I don't think it's not as biased as most surveys are biased, I think.
Right.
Yeah, I wanted to add, like, what about like adding algo binaries to that? Can we kind of like connect algos to say the helium stars that we're seeing in the Gaia post-mass transfer stars? Can we like connect them and say something about mass transfer more generally, or is that it's completely different physics?
Yeah, just to add on to that, but how about blue stragglers? How about STB binaries, the white dwarf main sequence systems that we heard about this morning, the post-common envelope binaries, the double white dwarfs, right? There's many more post-mass transfer, I mean, low mass populations, but in general, they're a little bit easier to find.
To go back to Likke's comment, I think that it's an encouragement for theoretician and observer to work hand in hand, because normally observers should know the selection function much better, even if they do not necessarily publish them, but they should be able to recreate them. You wanted to comment on Bloom?
Bloom, and generally, I think, I don't think spectroscopic surveys necessarily have to be that biased if you select them carefully, or yeah, kind of related to what Hugues just said. We have a survey in the SMC, I guess. I didn't want to actually comment on it. But no, I'm not going to say that. I'm not going to fall into this trap. We have a survey of massive stars in the SMC, which is, but the spectroscopic survey. But
bias control.
Publish your survey selection.
yeah, good. So let's do that in paper one.
Your code out for it.
Yeah.
Because it's damn near impossible to mock that up ourselves.
Yeah. But I just wanted to also mention Gaia. First, it has a limitation, of course, of being in the galaxy, and secondly, you're impacted by, for example, the very variable extinction, which is, I guess, more difficult to model. So I understand what you mean, but I think Gaia also has its limitations. Yeah.
But then again, like white dwarfs, you can see out until 100 parsec, right? You have large populations at relatively close by distances.
With Gaia? At the moment?
No, just white dwarfs.
Oh, white dwarf.
Right? Then you don't have the issue of the extinction so much, because you can make actually a volume limited white dwarf sample that is complete out until 50 parsec, and some people even claim 100 parsec. So, I mean, complete samples, this is something we dream about, no? No selection effects.
I was just going to say that looking at these local populations is really interesting, but I think that there's also a lot that we can gain from looking at things that are at much farther distances and probe other environments. So like supernovae that are expected to be part of binary systems. This does introduce more selection functions that we don't quite understand, and necessarily knowing how to go from the chemical profile of the star post-mass transfer to the observational features is also uncertain, but these are helping us probe much larger distances than the Gaia binary. So kind of using them all together at the very end will be helpful.
Let's move on. Okay. Sure.
Go for it.
Yeah, just a quick comment on volume complete samples. The hot subdwarf B volume 500 parsec volume complete sample came out a couple of weeks ago, and they have some super interesting results. And these are quite extreme post-mass transfer systems, so that's a great thing to check out.
Okay, with the assumption that non-Wolf-Rayet Helium stars come from binary interactions, how do observers distinguish between a Wolf-Rayet and a non-Wolf-Rayet star, and how can it guide us to actually distinguish also within stellar evolution codes like MESA? I mean, what are the chemical profiles or whatever it is that we can say, hey, this is a non-Wolf-Rayet Helium stars in my simulation?
Domer, you're just next to it.
I mean, for observers to distinguish non-Wolf-Rayet from Wolf-Rayet, it's very easy, because Wolf-Rayet stars are a spectral class of stars with strong emission lines. So once you see that, you call it a Wolf-Rayet star. If you don't see it, you don't. And the difficulty is finding the non-Wolf-Rayet-like ones, because they don't have these strong emission lines. So that's the sort of sample that Bethany and others are working on. So I don't know if you.
Oh, but whatever emission line, I mean, as long as we have strong emission line, is a Wolf-Rayet star. Okay.
No, so you want a hot star, broad, strong emission lines, and even then you might have some funny things, and Bethany is showing you a plot.
This is like divided by 5 because of how big it is.
Okay, I see.
Probably the
real
version of the cartoon. Okay, a big jump.
That's for the cheap version. If you want to have the accurate version, you go later ask Bethany. But yeah, Wolf-Rayet by definition is an emission line spectrum. That's the observational definition. Among the Wolf-Rayet stars, we have the classical Wolf-Rayet, which are the ones that we like. The massive stars with strong winds, or not necessarily massive, sorry, but the stars with strong winds. There's also other emission line stars that have been flagged as Wolf-Rayet, like the core of planetary nebula, Wolf-Rayet type stars. We do, some of us. No, but so Wolf-Rayet is an observational spectral class, which is just based on looking at the spectrum. And then after that comes the interpretation of it, right? But what we often assimilate a Wolf-Rayet is a compact star with strong luminosity that creates a strong outflows, so stellar winds.
But just to add to this, I guess for a person doing evolution models, you don't have this information necessary. You don't know how the star would look like. You need to assume some mass loss rate or something like that. So for this, I mean, there are different criteria. You could, for example, consider the luminosity or luminosity to mass ratio or something like that, which is a metallicity dependent thing.
Yeah.
Or you could self-consistently compute the spectrum given a mass loss rate, but that's a lot more work. So
look at the Eddington factor.
Yeah, that's my point. So you will be comfortable if I say everything above an Eddington factor of 0.5 is a Wolf-Rayet and everything below is non-Wolf-Rayet. I mean, just hand waving.
We need to compute it specifically, but you could probably get some recipes. Yes.
Okay.
Nebula or something else you wanted to say?
Yeah, Mathieu said he was.
I mean, I brought up the nebula. We kind of discussed it a little bit with finding the environment of the post-mass transfer. They're just finding the environment of the during mass transfer, which
I don't know. We found what we think is a merger surrounded by a nebula. That's going to be published soon.
Massive.
Massive. I don't know, 4 no stars, so 20 solar mass, 30 solar mass.
Massive, proper massive.
Massive.
But you mean the nebula is not because of the merger itself?
So that's our interpretation. What we found is we have a long period binary system composed of 2 stars that are not supposed to have interacted because the period is 20 years. But we found a strong mass discrepancy in the system, and the one star that is younger is also magnetic, and there's a nice nebulosity, and the abundance in nebulosity is not compatible with anything you can produce by regular winds of stellar evolution or rotational mixing. You probably need to drag out some of the material from the core, which you could do, according to Fabian's and his team, through the merger mass loss. And the dynamical age of the nebula is about 15,000 years, if I remember correctly. So it would be a recent merger. It's going to be published by Frost et al. Soon, as soon as the editor is finishing making 1,000 comments.
Is the main star still out of thermal equilibrium?
Sorry?
Is the merged star still out of thermal equilibrium?
We believe not. Is the merged star outside of thermal equilibrium? And we believe it's not. We couldn't find any evidence for it.
I had one more thing, I think, on this slide. When we were talking about the stellar response, we said, do we only need the mass radius exponent? I was thinking about wind slope overflow. Do we need a bit more information? What do we want for wind slope overflow, Shazena?
Oh, I think that's it. The elephant in the room for a lot of the discussion is that all of the stellar evolution calculations that we have here also include just mass loss from the star. And you can put up any plot of anybody's model of mass loss, and you can have orders of magnitude difference. So your masses of your stars are already affected before you even consider interacting with a companion. You already have one big problem. And then the actual wind mechanism is also when you are running the wind models, it turns out that having a companion nearby affects your wind. And so how to include that properly is a big question. I mean, we're working on it and we're trying to run different things, but I think it will have a big effect on, stabilizing things in some sense. You can avoid common envelope if you can transfer a lot of mass by winds while you're wide, and then you can get closer and then maybe do Roche-Loeb overflow. I don't know, but yeah.
Why does a companion affect winds? Is it because of tides or?
The
Why,
question
why
was
does the, yeah, sorry.
Yeah, why do winds affect the companion? Is it because of tides?
Well, so the companion has some gravity. And for example, in AGB stars, where I think this is a big problem, if the companion, the wind driving happens in several steps. So it happens not immediately at the surface of the star, but some distance away. And if the companion happens to be orbiting within that wind acceleration zone, then it's going to change what you would get from just having a single star. And so I think we don't really understand that very well. In AGB stars, where we have pulsations, which create shocks, and then the shocks, you get cooling behind the shocks, and the shocks form dust, and then the radiation pressure of the photons drives the dust out. But if you have a companion orbiting nearby in that zone, the companion will change the density, it will change the temperature of the medium there. And so you can have condensation there, maybe more than you would, or you could completely heat up the material and then have no dust. And so your wind will really, really change. And if you, I think in the pop synthesis models, I think the question is, what are people really assuming when they do Bondi-Hoyle-Littleton wind accretion? They assume some velocity, 10 kilometers per second, 20 kilometers per second, but that's the terminal velocity far away from the star. And is that even a valid thing when you have, talking about mass transfer of a companion near you're nearby your star? The wind velocity should actually be probably quite lower, but it could be different. And then in the massive stars, it's even a bigger problem.
Mathieu, do you wanted to?
I just wanted to add that this is also potentially a problem for line-driven winds and massive stars if you're on much shorter periods. But like models of gravitational wave progenitors that go chemically homogeneous, that have an orbital velocity of 600 kilometers per second, those you cannot compute assuming a fast wind for the non-conservative stuff, because probably the orbit is within the acceleration radius of the wind, and that changes the driving. And again, it's not pulsation, shock, dust, but it's the same logic.
Yeah, so in the massive stars, you have two sort of acceleration zones based on the opacity bumps. And so exactly that, you can have the companion orbiting within the wind acceleration zone. So what exactly are you assuming for your wind velocity when you do Bondi-Hoyle? And in any case, the Bondi-Hoyle-Littleton formalism is really valid for when you have, very fast winds where you don't have strong influence of a companion. So I think it's a big problem. Plus the radiation. And then there are winds from the accretor, sorry. Something that Brian was mentioning, the radiation from in CVs, but also the winds from the disk can stabilize mass transfer. People often invoke this in novae to try and have them stable. So winds and mass loss, I think, are a big problem all around.
Oh, I'm also wondering if, Shasrini, can you please, my takeaway for like wind mass transfer is that also the wind need to be kind of dusty. So AGB stars is valid. How about RGB stars? The wind is not that dusty. I'm wondering, yeah, any comments that will be super helpful.
I think in the RGB, it's a little bit, so there are two things. It's a little bit easier because the mass loss rates are not so high. So that hopefully the effect is not so bad. But then I think the uncertainty of what exactly is the mechanism is a whole nother. So Alphen waves, there's a lot of other processes that people invoke, and I think we still don't know. And I would say that that's true also of red supergiants, where the turbulence plays a role, probably some kind of Alphen waves. I don't know. Yeah, it's.
When we are talking about mass loss, either through stellar winds or through the inner Lagrangian point in the binary, what's important is what is happening close to the surface of the mass losing star, where the velocity is first small and then increases up to the critical point when it reaches the sound speed. And this is the region which influences then the mass loss rate. What happens beyond the critical point where the flow is supersonic is not so important, because if the signals are propagated at the sound speed, and so what happens beyond the critical point cannot be, the information cannot be transferred to lower radius, let's say. So that's my point.
Yeah, forgive my potential naivety as a more single stars expert than binaries, but what happens when the velocities reach sort of sonic velocities just because of the turbulence near the surface of the star? Because this is what's happening as it's, especially in the massive luminous regime, this kind of, the surface convection or subsurface convection hits transonic velocities even, below, beneath tau equals 1. And especially on the red supergiant branch, this can be pretty significant. So what happens when the whole envelope is in causal contact, but it's still supersonic?
Flows away. What's the answer, Jared?
That was a question. I guess we'll wait for Jan Fay.
Yeah.
So I guess this situation has to be non-stationary then. And then the answer is that we don't know.
So I would say that that's exactly the point with the AGB stars. It's non-stationary. Your sonic point is changing, so you can't make this nice. Once you hit the sonic point, it's going to flow away. The material falls back. It's cooling. It's doing all sorts of crazy things. There's shocks, dust. We don't have this nice.
Oh, there's a comment over there. Just go for it. And then...
Okay, it was to circle back to what you were saying before. But so, I mean, okay, everything is unconstrained, but let's say that you had to give an estimate now for population synthesis, otherwise Earth explodes, okay? So how much you would increase or decrease the AGB wind mass loss due to binary interaction? Yeah, I mean, that's driven or light driven with the interaction of another star. How much you would increase it?
So we have a plot of this for wind Roche overflow. It can be 50 times higher than Bondi-Hoyle.
Wow. Accretion, right?
The
Accretion efficiency.
Yeah, the accretion efficiency can get 50 times what you would expect from Bondi-Hoyle if you take 10, 20 kilometers per second. Okay, so there's a distribution. It agrees better with Bondi-Hoyle in the shorter orbital periods. Then there's a peak, and then longer orbital periods again is a bit better. But I mean, 50%, yeah, it's a lot. You can do.
Okay.
It's not.
Sorry,
it's not only
not
the
50 times.
50 times. Okay.
50 times. Yeah. Sorry. Tired.
One quick comment that I wanted to make, it's okay to say that we have this problem in AGB stars because of pulsations and so on, but this is technically also true with red supergiants. We observe that all of them pulsate, as far as my knowledge, that the majority of the ones that we observe, they have not only one, but they have many orbital and many pulsation periods stacked, and their radii can change by significant factors. So then this would also complicate the view on how wind moves in red supergiants, let alone how the turbulence itself adds to this. So I just wanted to point out that the situation is even worse.
I am very curious about this question that Hugues actually wrote down. So what do we think about circularization of systems? Is it the case that every mass transferring system will circularize before the onset of Roche-Lobe overflow?
I can say, for example, that with, for example, KC binaries, they're so wide that there is just no way for circularization to happen before mass transfer. So I would expect that at least the very beginning of mass transfer should be very eccentric. Well, at least with how eccentric the binary was initially. Then how it evolves, I'm not sure. But for the very wide binaries, it should be eccentric initially.
Yeah, oh my God. I agree with that. I think this is actually like a super complicated question because the way that your tides are dissipated depends so strongly on your structure of your star, and your structure of your star can be incredibly different at various different times of onset of overflow. But I guess the important things to think about are the time scales. So broadly speaking, the more massive your star is, the more quickly it's evolving. And so the less time it has for the tides to work. And tides are broadly a pretty inefficient process. I mean, maybe Meg can also comment on this a little bit more, but it also seems that out of often the more detailed that you calculate the tides in, this isn't universally true, but a lot of the time, if you are a little bit more careful about how you treat the tides, then your tides get even less efficient. Except if you have a resonance, yeah. So if you have like a highly eccentric system, so the tides are really efficient if your eccentricity is above like 0.6, 0.7. And we also kind of see that in the observations. You don't see so many of these extremely eccentric systems, but you do see quite a lot of these moderately eccentric systems. And it also makes like one of the huge differences is if you have a convective or a radiative envelope. So if you've got a big convective envelope, then your tides are pretty strong. But even in this case, even on the RGB, a lot of the more massive end of the RGB, unless you're in a really close orbit, you don't even necessarily expect circularization to happen then, because the AGB lifetime is, the RGB lifetime is pretty short for these really massive systems. And also the bigger RGB stars have a less deep convective envelope, so they also have less of a dissipative region. So I don't want to say like never, but I also don't think always is the right answer. And then also we know that loads of stars are in higher order multiples, and then that just gives a way for the eccentricity to be excited. But even in the binary case, I think that care should be taken, unless you're dealing with these really, really close systems where you have like orbital periods of some days or something like that, then I think it's probably okay. Yeah.
I wanted to quickly add on for example, whether white binaries are eccentric or not, because there is one famous example of VV Cepheid, which is a red supergiant undergoing episodic mass transfer with a companion. And it's an eccentricity of 0.3, and it's an orbital period of 20 years. So now I'm not sure what's the stage currently of the binary, but if anyone could observe it in the near future with very high detail, because if we can observe how the mass transfer actually, well, I don't know how observationally this is seen, but if we can get like a profile of the mass transfer rate, then we can build models and fit and perhaps build a better model for how mass transfer would work, considering that this is an eccentric binary to begin with.
What about the opposite? If, as an observer, I find a binary with a period of 100 days, which is exactly zero eccentricity, can I assume it has been through Roche-Loeb and circularization? 100 days, 50 days, whatever.
Then yes.
So then you intrinsically assume that the universe doesn't produce anything circularized, that there's not a good reason to circularize.
I mean, it's kind of fine-tuned, right? To get it radically zero.
Yeah, but
star formation, you can circularize already, right?
Yeah.
Yeah.
Are those periods?
Yeah. 50 days, of course. I mean,
but then all of them should be circularized.
No, why?
Mass ratios.
You can never make a circularized.
Mass ratios.
1 to 2.
Maybe. Momentum transport.
1 to 2. That brings us on another question. I don't know if this is a good time, but what happened on the premium sequence?
Oh. Yeah.
There's some improvements.
I think on the pre-main sequence for lowish mass stars, like less than a few solar masses, they seem to synchronize below, circularize if the orbital period is less than 8 days. That's about it.
Those are fully convective with equilibrium tides that are strong, right?
Yeah.
And that's observed as well. I see.
Is there a massive counterpart to that?
On the Premium sequence, you are not supposed to be able to fit a massive star which is bloated in a short period binaries, but we see many short period binaries.
Where do you come from?
Your guess is as good as mine.
Well, but
They're not able to fit in the orbit if you assume a thermal equilibrium radius, right? So maybe that's the wrong assumption, simply. You keep on accreting, you keep on being driven out of thermal equilibrium. That usually makes you bigger, so I don't see how that helps, really, but...
There is some other observation that show that we are missing the short period system in the very young clusters, which means that our assumption about the initial conditions are probably not correct. Just a hint for population synthesis.
that's a factor.
So I think last time was at I remember at the conference in Munich that there was some discussion about this, and Max Mo was saying that maybe it's possible to explain that with an evolution in eccentricity and not in binary separation. So what's your opinion on that? I don't know. They were saying that basically you go from eccentric systems to circular systems, I think, and that could while in the thing that you mentioned, I think there was a minimum period cut, and that could change the minimum period cut.
Yeah, so I missed half of the conference in Munich, so I missed that specific talk. I think it's quite difficult because you would need to start with very high eccentricity for it to work. I would need to compute it to be certain, but I think you would really need to start with everything very eccentric, and then it would work. And you cannot make those eccentric binaries with capture because first, at least in the galaxy, the stellar density is not high enough. And also it's very hard to make a short period system with capture. You make systems of periods of years, not days. You wanted to add something, Pablo?
Floor, I think.
No, you good? Okay.
Floor.
Yeah, I also have a follow-up question actually on that, which is like, people like Sally Ooi and others from observations are saying like, oh, maybe all field binaries were once upon a time formed in some like star clusters. Would that impact, for instance, how we, like what constraints we put on like binaries that we observe and their properties?
So I agree with Sally that probably the vast majority of massive stars are formed in clusters. There may be some that are formed in isolation, but those numbers are going to be small simply because it's not efficient. You form tens to hundreds of stars in clusters, and you only form so many in the field simply because of the amount of mass that you have, right? What was the subsequent question?
Yeah, like, does it impact the properties, right? Like eccentricity distributions that impact like how you infer mass transfer?
I would assume not so much. The stars that end up in the field are probably stars that have been ejected either by dynamical ejection or by supernovae later on. Given most of the stars stays in clusters on association or they dissolve very slowly, right? I don't think it makes a big difference. Want to pick another question? We have 7 minutes left.
Can I ask, how about the blue stragglers? There's some really cool blue stragglers where they find the companion, the white dwarf companion. Aren't they giving us nice clues about stable mass transfer?
Yes, so I've done a lot of work using HST to actually measure masses for white dwarf companions to blue straggler stars. And we're also starting to do measurements of white dwarf companions to what we're calling blue lurker stars. So these are actually kind of post-mass transfer stars that are on the main sequences of clusters. And so we are getting this mass this way. And the nice thing about clusters is that, we know what the mass of the donor star was, because it's a cluster. We know now what the mass of the white dwarf is. We know what the mass of the blue straggler is. If you observe it for long enough, you can get orbital periods for these. So, we're able to provide really, really good constraints, is only for a few systems because we have to observe them really extensively. But I think in these sort of case studies, we are able to put a lot of really good constraints on, what was the initial mass ratio where we were getting stable mass transfer? What is the outcome? What was the evolutionary state of the donor? So, I think the con there is that the sample size is not big. We can't do this across like a huge range of masses and evolutionary states, but we can get these kind of glimpses that are very, very well defined for a few systems like this. And so we are doing that.
What type?
Are any of them?
Many questions. Are they eccentric?
Yes. In fact, we don't see post mass transfer blue stragglers that are circular unless they're very low metallicity.
How few samples do you have?
How big is your sample? Lika asks.
It depends on exactly what you're talking about for our sample. So one cluster that we've studied really well is M67, which is kind of like the best studied open cluster there is, debatably. And there, we've done the blue stragglers. There's like, I think there's about 15 or 20 of them. Blue lurkers, it's comparable. So there are as many stars hiding on the main sequence that are post mass transfer as there are blue stragglers, just to give you an idea of the magnitude there. We've done this in, we've done these HST studies also in NGC 188. So that's the other one that's been really well constrained. That's an old cluster, like 6 gigayears. It starts to be harder to do this for like very massive clusters because we can't see white dwarfs next to a massive star unless they were like absurdly young. So this is giving us kind of a glimpse into how mass transfer works in fairly low mass systems.
Quick question, how massive are your white dwarfs?
Yeah, so this is one of the surprising things that we've found looking at the white dwarfs is we were expecting that they were AGB mass transfer. And some of them do seem to be like, 0.5 solar masses or so. But we also find things that are mass transfer at the tip of the RGB. So 0.4 to 0.5 solar masses. And I suspect that actually what we're seeing, and this is kind of speculative, so we'll see if getting more data makes this pan out, but it looks like among the blue lurkers, there's actually more stuff that went through mass transfer on the RGB. So it's kind of pointing to this idea that mass transfer at the RGB tip might be, either its mass transfer is occurring onto lower mass accretors, or the mass transfer itself is just really non-conservative.
I also have a question. Sorry for shooting all the questions towards you, but in open clusters, does the velocity dispersion of the cluster give you some upper limit on the pre-interaction period that binary could have? Because you have the masses from the white dwarf mass and the observations, but the initial period would be very important to constrain. And I just don't know if in an open cluster that constraint is really valid.
What do you mean? Why would the constraint not be valid?
Well, if there is very little dynamical interaction, you have a lot of room, it's very fluffy, diffuse cluster, it might not mean much velocity dispersion. I don't know.
Oh, so we have actual like orbits, like time.
Oh, but I want the orbit before they interacted when it was not a blue straggler.
Gotcha. Okay, so we don't necessarily know what the orbit is pre-mass transfer. What we do know is we know the core mass of the white dwarf. So we can tell you how large the star was on the RGB or AGB when the mass transfer ended, if you believe the core mass radius relation for red giants, which is pretty well established. So from that, we can tell you like what should the orbital separation have been pre-mass transfer,
But that's just a lower limit on the separation. Is it?
They have the mass.
No.
Yeah, I mean, so it depends. Like, so we can tell you what the white dwarf mass was when mass transfer ended, which tells you what the radius of the RGB star was when mass transfer ended. Yeah.
The only thing that you don't know is how massive the companion was.
Yeah.
Right. So that gives you two
Yeah,
options.
and I will say one interesting clue for how massive the accretor was that we've been working on is that the core depletion in the main sequence star is, we think, left imprinted on the blue straggler. So in other words, if you take something that's still really rich in core hydrogen, you accrete onto it, the blue straggler ends up close to the ZAMs. If you take a companion that's close to the turnoff, accrete onto it, you see that the blue straggler is closer to the TAMs. And so, you know, there's some uncertainties there for like remixing in the core and things like that. But it really does look like you can put some pretty good constraints, especially for blue stragglers that seem to land far from the ZAMs. You can really say with pretty good confidence that thing had a pretty depleted core before mass transfer began.
All right, I think it's going to be time to wrap up. If you feel urgent questions, there's more space on the whiteboard there. You can write them down, and I'm sure that we will discuss them in the next 2 days. Do the organizers want to have a final word?
Just a quick announcement thank you again for all the speakers today. So maybe a round of applause.